Okay, in this video I'm going to take a look at how to truncate the zero region of Leisen Reimer Tree. So generally speaking, binomial trees, whether Cox-Ross-Rubinstein or Leisen Reimer, entail generating a stock price tree based on up and down movements that we estimate from parameter inputs. The parameter inputs here follow closely Black-Scholes model. Major difference between these parameter inputs and Black-Scholes is in a binomial construction we also have to specify a number of steps in the tree. But once we have those parameters, then we can set out an up and a down factor that we apply when generating the stock price. So if the stock price initially started at 100, we multiply by this up factor or multiply by this down factor to estimate the different nodes that we present here. In addition to that, when we work out the value of the call option, there is obviously the binomial tree, but then we have to set out a framework for implementing what's known as backward recursion, where we start off with the intrinsic value of the option in the final set of nodes, and then we pass these nodes back sequentially using a backward recursion technique. In the case of Leisen Reimer, that follows closely Cox-Ross-Rubinstein. We take the value, we estimate the value of P, which is a probability measure, and we apply that to the stock price, to the value of the option if the stock price goes up, and then the value of 1 minus P again, is applied to the value of the option if the stock price goes down. In the intrinsic estimation, which occurs in the final node, when we're estimating this tree, once the stock price falls below the exercise, price here, 100, then we get a zero region, and that zero region will persist back through the tree. The zero region has no impact in terms of valuation here. Once we have zero values in terms of the tree here, once we implement backward recursion, 0 here and here will imply 0 here. But those zeros will persist. But in terms of impacting here, in terms of valuation, there's no direct impact. So excluding this region excluding the zero region will not foster any change over here, but it will speed up estimation because much of the backward recursion activity that's going on is being applied here in the zeros. But we obviously know that if we take these two values and then apply that backward recursion, if we have 0 here and here, the value must logically follow that it's 0 here as well. So once zeros are here, we don't have the effect of the zeros here will have no impact here. Okay, so excluding this region then would make the estimation more efficient, and designing a strategy that allows us to exclude the zeros then is worthwhile in the sense that it will expedite the Leisen Reimer estimation. Now, to look at, first of all, before we examine how to exclude the zeros, we might again just revisit how to estimate the estimation of the Leisen Reimer tree. And again, in this instance, I follow Volupte, I follow Espenhogue in terms of setting out dynamic recursion, and we make use of dynamic memory. So if you like, the code that we have here in terms of estimating the intrinsic value of the options is really just applied to the final nodes. So if you like, we set up a loop. The loop runs so that we go from 0 to n, and we increase in steps of 1. And then for a call option, z is equal to 1. And then we figure out the value of the stock price by setting out su to the power of I by by d to the power of n minus 1 negative k, and each instance I is changing. So for instance, go back into our tree again. That code is generating this ultimate set of nodes, or the nodes in the final step, and we go from 0 to n. N, remember, was we had set out as being 15 here, right? And we run that, so we pull out 16 values. The 0 plus the 15 others make 16, and we pull out all the intrinsic values in the option. Then the next step in terms of estimating the American option, which we start off with here, involves taking the maximum of S minus K, the stock price, the relevant stock price, minus the exercise or the time value, where A10 is P times the value of the option stock price goes up, plus 1 minus P times the value of the option if the stock price goes down, and then we multiply by, this is the discount factor, E negative RT. So the time step, we discount for the time step back to here. Okay, so that's the, again, looking at the code in terms of that estimation. The intrinsic value, the final set of nodes are estimated, the terminal nodes are estimated using this small snippet of code. To then estimate the backward recursion, we have to set up a loop where J, again J is the, J and I are mutually referencing each other, but J in principle is the number of steps in the tree, and I represents the number of nodes in the column. So if you like, the number of rows, the number of columns. In each instance, as we do the backward recursion, I shrinks by 1. So that's the nature of the binomial tree. I is constantly shrinking and is constantly being resized. So when we perform the backward recursion using the approach implemented by Espen Hogue, we start off in the pentultimate node, pentultimate column, n minus 1, not n, so n minus 1 is 14. And we say j is equal to 14, and we go back to 0, and we reduce that by 1 each time. So basically we're setting out the estimation such that we estimate this n minus 1 column. Then we go back to n minus 2, n minus 3, n minus 4, until we get back to here when j is equal to 0. Okay, so if we look at our code again, we go back as far as j equal to 0. Then at each j, we set out the relevant number of i's. So we start off with I being equal to 0, and we go up to j. So when j is equal to n minus 1, I will go from 0 to that n minus 1. Okay, so in other words, when we're here at j equal to 14, then we run another loop in the estimation for the backward recursion where I will change and go from 0 up to not 15, but actually I goes up to 14. And then once we perform those estimations, we pull back to n minus 2. So j is equal to 13, and then we run the valuations going from I equal to 0 to 13 in our estimation. Okay, so in other words, we're running the loop, a double loop, where we sequentially we reverse back through the j's, and at each j we generate a set of i's that we estimate, and then the value of the option then is set out in terms of i's, and that array keeps changing, right? The array, if you like, keeps resizing. We initially start off with an array of 15 plus 1, 16, but it's going to resize as we go through the various loops we've presented here. If we estimate the European option, we don't worry about taking the intrinsic value, we just pass the values back. As we pass the values back, the I option value I, this array, will absorb I plus 1 and I. So at the following estimation in the preceding j, once these values have passed into option value I, that becomes the new option value I, and then that in turn gets exchanged again as we go back through j again. So in other words, the structure that we have here in terms of the estimation is highly efficient in terms of we don't store in the entire value of S in a 2x2 and two-dimensional array. We generate the stock price sequentially, we generate the option value sequentially, and those values pass back. So very little memory is absorbed in storing a huge stock price lattice that we typically have in static type models. Okay, so in the European option we have these values being passed back. We can take a look at that in terms of our tree again. In the European option, okay, we can get rid of this, no value. Okay, we estimate the value, the intrinsic value of the tree, and then we get the time value, and again the time value can be obtained by taking by discounting df, the discount factor, which is multiplied by what's in our brackets, and then we have p and 1 minus p, and then the value AQ20, the value of the option of stock price goes up, value of the option of the stock price goes down. Okay, and that's done sequentially all the way through until we get back here, and we can see that the value here is consistent with the value I've obtained from Espenhogue VBA code, right, for a 15-step tree. Okay, so we go back again, we take a look at the American tree. It's much the same, except we add this term, maximum of S minus K. In terms of truncating the zeros then, we haven't done that in this particular in this loop, because we started our tree with I equal to 0. So as we go through the dynamic recursion, I equal to 0 all the way up to I equal to j, which in this case would be n minus 1 in the penultimate column, we basically not only estimate these values here, but we also are including this range of values here. And that can be quite wasteful in terms of computational time. And if we had a way of excluding that, then it would improve the efficiency of the estimation time. Okay, so to observe that in practice then, how do we do that? Well, one approach we can adopt here is to change our code, to change the structure of the loop. Okay, so if I go into the dynamic code for a moment here and take a look at, in this instance, this code is exactly the same as the previous code, except I'm truncating the 0 region. And we'll see in a moment in the next video how that truncation of the 0 region will speed up estimation.